Hi everyone, and welcome to our Data Center Knowledge webcast, How Artificial Intelligence and Machine Learning are Transforming Data Centers, sponsored by Raritan. If you have any technical difficulties during today's session, please press the Help widget on your player console to receive assistance in solving common issues. If at any time you're having audio difficulties or issues with advancing of the slides, please hit your F5 key to refresh your webcast console. Today's web seminar is being recorded and will be available on demand for 12 months starting tomorrow. You'll receive an email when it is ready. And with that, let's meet today's speakers. Scott M. Fulton III is a regular contributor to Data Center Knowledge and provides insightful coverage of news, events, and developments relating to the design, implementation, and management of large-scale data centers worldwide. Paul Mott is the Global Technical Product Manager and Xeris Technology Platform Expert at Raritan, which is the Data, Power, and Control Division of Legrand. He has over 10 years of experience in the IT industry and has been with Legrand for over 8 years. Mike Sabata is a solutions architect at NVIDIA and is a technologist that has architected and delivered server and storage products for some of the largest cloud and HPC customers. And with that, the floor is now yours, Scott.
Thank you, Jennifer, and hello, everyone. It's a delight to be joining you today. And I absolutely appreciate all of you taking time out of your busy day to join our discussion of power and intelligence and whether the twain shall meet. First, a bit about myself, but not too much. I've been a technology journalist and author of 17 books on topics dealing with enterprise IT, software development, applications, and distributed systems throughout the last 35 years. I have the distinct honor of contributing to a publication with knowledge in its title. I produce online features and contribute to webinars for a knowledge publication. So I should know something about knowledge, and you'd think I would know something about intelligence. At least one would hope. Here's the thing about intelligence. Once you have enough of it, people stop noticing after a while. Folks tend to appreciate it when something is intelligent that they didn't expect could become intelligent. Artificial intelligence is exactly that, smarts where you don't expect smarts. I'm frequently asked, is there a way to leverage AI to make data centers work better? There are some vendors who say yes, and I've spoken with them. You can read more about this question in this Data Center Knowledge Special Report. Most of what they've told me boils down to these three things. First, you have to know what normal data center behavior is. A machine learning model is, first and foremost, about learning. You can teach an algorithm to recognize text, but to teach it what an anomaly looks like, it has to know the patterns of normalcy. Second, you need to know about the software your data center is running, not just names, but where those workloads are hosted physically, which servers, which zones. Higher intensity workloads generate more heat. If you've determined in advance which servers will be the hotter ones, then you need a heat management strategy for those servers. Ironically, AI and machine learning are among the hottest workloads you can possibly run. Also, don't focus on one region or zone. Maybe the hottest zones may need the most intensive treatment strategy. But if you lack awareness of your facility's electricity and workload distribution, those systems you've relegated to the back burner may eventually overheat. The key word in this last sentence is awareness. Before you can make use of artificial intelligence in your data center environment, you're the one who needs to understand that environment. Someone has to train a machine learning system as to what the patterns are. And someone needs to know enough about how those patterns are applied to make sense of anything an AI-equipped DCIM system may suggest. This is the National Renewable Energy Laboratory, or NREL, located in Golden, Colorado. NREL's researchers perform physical and virtual research on alternate power sources and on future power distribution systems such as the power grid. such as the smart power grid. This is where Eagle is being built, and its predecessor, Peregrine, was built. Eagle now ranks number 35 on the list of top 500 supercomputers worldwide. But its goal is not so much to top that list as to be the most efficient. In January 2016, a team of NREL researchers published the results of a study looking into whether high-performance computing techniques could be used in the management of high-performance computers. Could a set of algorithms optimize the distribution of workloads throughout a system in such a way as to substantially reduce a system's peak power draw, while at the same time effectively managing its own power in the process, sort of like upgrading the legs of a marathon runner during the marathon? Here's what they were up against. Each of the points on this chart represents the top 25 high-performance supercomputers at the time of the experiment. The more performance a supercomputer delivered, naturally, the more power it would be expected to consume. In 2014, it appeared the power curve for a supercomputer capable of performing at 1 exaflop, that's 1 billion calculations per second, would be here at 100 megawatts. Where the U.S. Department of Energy wants it to be capped is here at 20 megawatts, about the same power consumption as China's Chang'e. Here's what the NREL team did. They created two classes of power profiles for a particular type of math job. The job class on the left is the naive class. It had not been optimized for power efficiency. Meanwhile, the job class on the right, the efficient class, was geared to utilize Intel's CPU power optimization, yet still consumed at least twice as much wattage. NREL developed an algorithm that scheduled the naive class to be run during periods of low power consumption, such as at night. They scheduled the efficient class for high power periods, where the on-campus photovoltaic power generators were most active. As a result, they gained 250 kilowatts of power efficiency overall. They reclaimed 1/4 megawatt without altering the workloads themselves. The NREL team did everything they were supposed to. They scientifically defined what their normal power consumption rates were through careful observation and measurement. They made profiles of their workloads to the extent that they could. And they envisioned a system where all their workloads were included in the scheduling system. But AI had nothing to do with it. In fact, much of the data the team utilized for other workload classes was based on calculated estimates. As they stated in their report, unfortunately, we are currently unable to holistically measure the complete micro-level energy footprint of a scientific application. The most important workload class in their arsenal, and they were just guessing. If they had used machine learning, specifically the same types of AI algorithms used to recognize patterns in printed text and fluctuations in currency markets, could they have inferred what their application's power footprints should be? Here is the best book on artificial intelligence that was ever printed. I bought it 40 years ago from the electronics bookshelf of a Radio Shack next to the Shortwave Listener's Handbook and the comic books about 50 things you can do with a 9-volt battery and a paperclip. And because I was consulting with Radio Shack at the time about how to demonstrate their new 16K TRS-80 computers, I picked this up for half price. Best $4 I ever spent. What made this book so wonderful is that it actually explained and diagrammed AI algorithms. But also, there was Neil Graham's perfectly brilliant and succinct definition of AI, some form of which I've consistently used now for 4 decades. Artificial intelligence, he said, is the branch of computer science devoted to programming computers to carry out tasks that, if carried out by human beings, would require intelligence. Put another way, if a task was done well and you start to attribute it to a smart person, but it was really performed by a computer, then it must be AI. It doesn't matter what the algorithm actually was. If you were fooled into thinking it was smart, that's enough. Maybe NREL did use AI after all. Then Graham offers a warning. This effect wears off. Once you get used to seeing AI, you stop thinking it's so smart and write it off as commonplace, ordinary, plain, normal. This is Jaja, a robot constructed by students at the University of Science and Technology of China in Hefei. Folks who've seen this machine say she sure seems smart. One reason, they say, is because they've seen her cry. Evidently, Jaja can emit tears. The type of AI we could use in the data center might not need a face or wear lipstick or cry real tears. Yet it might need something like a brain. For the last few decades, this has been the model for a digital system that developers say is something like a brain. This is a basic neural network. It has a system of digital neurons whose values are impressed upon by training events. Those events shift the weights attached to neurons so that if they feel those events again, they're more receptive to them. The weights make it easier for electrical signals to travel through the hidden layers of a neural network the same way repeatedly. Eventually, if you train a network to recognize a symbol when it receives a pattern of electrical impulses, the output layer will know how to reproduce those impulses when given that symbol. So, if we can train a neural net how to recognize a lowercase letter A, perhaps we can train it to recognize normal. Maybe we don't have to actually understand the underlying patterns that make a normal data center behavior normal. Maybe we just have to know that it is, train the network to send up a flare when it sees it, and plan a strategy around what happens if we don't see the flare. All machine learning is based upon a form of a system like this. The type of AI we could really use in the data center would give us insight, analytics, and some greater sense of awareness of how it manages resources. That leads us to the most important question we'll ask today. Do we really need AI to make us more aware of our power consumption? Let's face it, all electrical power runs through power components. We're already distributing our power components safely and efficiently throughout the data center. They've already started collecting data and logging it. And we've begun using workload orchestration through systems like Kubernetes to track and manage the server nodes and clusters where workloads are being distributed. Perhaps we can correlate the two. Here is a rack-level PDU. It looks pretty normal, but perhaps we could call it smart. After all, it has its own web interface for delivering analytics in real time. It reports its own status, its neuron value, if you will, through a legible front panel that doesn't require a PhD to interpret. It hosts its own hotspot mapping, meaning it networks with other PDUs in the facility to give you a big picture overview of heat generation. And it produces data in a format called JSON that's exportable to, of all things, cloud-based neural networks like Azure Machine Learning and Google Cloud AI. So maybe all this time, we've been imagining AI in the wrong direction. Suppose we build an AI platform from the bottom up with PDUs as our neurons. Maybe the answer to our power management dilemma going forward is so commonplace, so plain, so normal that we forgot how smart it was. This is as far as I go on our program today, and is where I hand off the baton to Raritan and Paul Mott.
Thank you very much, Scott, for that great intro. So my name's Paul Mott. I'm Raritan's Global Technical Product Manager, and I'm going to dive a little bit deeper into specifically power distribution in and around the data center cabinet. So really, when we look at intelligent power in the data center, why do we need this? So based on a 2018 data center knowledge study, we can see that rack power densities are really increasing. 67% of respondents actually saw that their cabinet power densities were increasing over the past 3 years. We can also see that the single-digit kW cabinet capacities are slowly creeping up over time, and this is ultimately going to be impacted even more as we start to see more machine learning workloads distributed across the data centers. Now, this is all great, but really intelligent power comes in to the point where it's really, really critical to understand power consumption and how that power consumption is becoming impacted and is impacting your power infrastructure over time. So when we talk about machine learning and how machine learning can impact intelligent power, we really kind of look at it in two different ways. The first is from a data science or really hardcore machine learning expertise standpoint, right? These types of applications may already have GPU-based hardware deployed in a data center already. They may already be running some type of machine learning and really crunching a ton of data to gain some valuable insights around anything from scientific research to weather patterns, what have you. The other is the more traditional enterprise environment. They may have more x86-based hardware, maybe no type of machine learning hardware at all in the data center, but really they are interested in potentially optimizing things and gathering more information about their power infrastructure today. So when we look at machine learning and the types of hardware that it runs on, it really becomes a challenge from a power and power infrastructure standpoint. Now, a good example is the NVIDIA DGX specs. Now, Mike's going to talk a little bit more about this next, but really I want to focus in on the power specifications of this device. Now, it has 6 power supplies and can consume up to 12 kilowatts per 10 RU. Now, this is a super high performance type of system. And really, you're going to be hard-pressed to find a power distribution device on the market that can handle one of these, let alone multiple. And in some applications, you might need 2 or even 3 of these to process some of those machine learning workloads. Now, few companies in the market can build these types of power distribution in the cabinet, but Raritan has expertise over many years building 50 kW plus cabinet power distribution, and we actually lead the market in that type of capability. Now, it's also important to have not just the PDU or the power distribution unit, but also having a technology platform behind that power distribution unit that can collect all of that data, can crunch it, and can deliver it to either a DCIM platform or some other platform so you can gain additional information. Now, we use a platform called Xeris, and it's a homegrown, completely developed by Raritan platform that spans across the hardware, the controller, all of the metering and monitoring algorithms, all the way up to the user interface and APIs that make this a completely open and distributed type of architecture. And we also span this across multiple product lines, so you have a consistent and reliable type of data center power infrastructure intelligence that you need to process things and support things like machine learning and high performance compute. Now that we have both the PDU and the platform to drive all of this, really we start looking at things that we want to acquire data on. And the first is power data. Now, on intelligent cabinet PDUs, there's several different points where you can acquire this data, starting at the inlet level, then going to the breaker or branch level, and then ultimately down to the outlet level as well. Now, being able to collect power data at that granular level really opens up a tremendous amount of insights, right? You can start to look at things like phase imbalances, potential circuits that might be becoming overloaded, and things like circuit breaker trips that might ultimately happen due to that. And it allows you to really plan and prevent a lot of unnecessary downtime, and then also look at things like maybe where you have stranded capacity or where you maybe need to add more capacity because you're running out. And then ultimately, all of this data can be collected and sent up to any type of DCIM tools that you might have. So that's the first type set of data that you can collect around intelligent power. Second is environmental data. So this is also just as important as power, especially when we talk about machine learning, because machine learning workloads, as Scott said, are going to generate a tremendous amount of heat. And we really want to understand down to the cabinet level where maybe things like hot spots and other type of environmental events can occur. Now, in intelligent power platforms, usually it's really easy to deploy small form factor types of sensors at the cabinet level to do things like temperature, humidity monitoring, airflow, differential pressure, and even things like water leak detection. Now, again, this is really important, especially in regards to ASHRAE standards, because it states that not only should you monitor things at a higher level, at a crack or at a row level, but also down to the individual cabinet as well. It's really, really important to, especially in these high performance applications, to know not what just your overall data center space is doing, but maybe what your high performance equipment is doing as well, to make sure, again, there's no any type of unplanned downtime, and you can prevent any type of issues from occurring due to maybe high intensity or high heat output from some of these devices. So those are the two types of environmental monitoring and power data that you can collect. Now, really, this can generate a tremendous amount of data. Each power distribution unit by itself can log up to 12 different variables per outlet. And then sensors can add another 10 different monitoring points per cabinet on top of that. You can layer on facilities data monitoring as well. There might be some higher level, either room temperature, environment, or power that you have as well. And this can lead ultimately to hundreds of different data points for every single cabinet, thousands per row, tens of thousands per cluster, millions of data points per data center. Now, this really is a data tsunami. So what do data center operators do with all of this? So the traditional approach really is DCIM. There's a number of different tools that are available out there on the market today, and you can take all of that valuable power, environment, infrastructure data, plug it into a DCIM, and start to really understand what's going on in your environment. You can understand things like where there might be hot spots, where you might have stranded capacity, where you might necessarily be overcooling or undercooling something, so you can make some manual optimization based on that. But all of this data is great, and DCIM is awesome, but really this discussion is about machine learning. So what can we do with all of this data that we're gathering, and really how can we apply it to machine learning? Now, isn't really all of this just training data at the end of the day? And isn't there some way that we can make use of it? So the answer to this question is yes, absolutely. And Google has actually proven this. Using their DeepMind platform, they were actually able to take all of this environmental and power data, plug it into a machine learning algorithm that ultimately self-optimized itself over time. They were able to see a 15% drop in PUE, which is the lowest it was ever at this particular large-scale data center. Now, that equates to a 40% reduction in cooling costs, which was a tremendous result from this effort. Now, over time, they noticed that there's a direct correlation to the amount of training data and the energy and efficiency that they were able to gain. And over the period of 2-3 years, you can see that the amount of training data that collected and the amount of efficiency increased. Now, all of this is available publicly. You can take a look at this on Google's development website, and they also have some more technical information. If you guys are interested in it, I highly encourage you to read up on this. It's very, very interesting, and I personally think this could have a tremendous impact for the future. So in summary, really, intelligent power and machine learning go hand in hand. There's a tremendous amount of insights that you can gather today, whether or not you're running machine learning natively in your data center, or whether maybe you have a traditional data center, but you want to start gathering more intelligence about your power and your environment. And the self-aware data center might not necessarily be a reality today, However, in the future, all of this data that you're collecting about your power and your environment are going to be crucial to any type of machine learning and optimization that may take place. And as always, Raritan and Legrand are the power experts that can build any type of high power density or any type of intelligent power that you might have for your data center needs. Now I'm going to kick it over to Mike, and he's going to talk a little bit more about NVIDIA and what they're doing to drive machine learning.
Yeah, hello there. Thanks everyone for joining the webinar today, and thanks for setting that up for me. ML in the data center is a huge trend. It's growing greater every day. The way that NVIDIA views ML is there's two primary phases. There is a phase to go and create a neural network, and then there is a phase to go and deploy that neural network. So the training is the creation of the neural network, and the inferencing is the using of that neural network. A neural network, there are many different types of them, and they have different longevities. There are certain neural networks that want to pick up new data every 10 minutes, every hour, every week, there is a temporal nature to that neural network. So for example, if a sports event is happening, then you actually want more inference engines to point to whatever that sport event is. If there is self-driving cars and there is an accident or a reroute of traffic, you want those inference engines that are being deployed in, or the maps, to be coming up with a different answer based off of something that is happening currently. ML performance has been increasing in visibility. So 20, 30 years ago, things like the TPC-C and the TPC-H benchmark were created to help characterize the performance of databases and data warehouses. ML-Perf is an organization that was created right around a year ago, and then about 6 months ago they released their first performance benchmarks, or their first submission benchmarks. So on the first round of submissions, they were very much focused on the training side. At this point, they don't have the inference benchmarks done, but we expect those to happen in the future. So, if you look back in history on what happened with the TPC-C and H kind of benchmarks, it drove significant innovation in the servers and then in the storage and in the software to go and solve those problems. I am very optimistic that this ML-Perf benchmark is going to do a similar thing for the AI community. In this benchmark, NVIDIA deployed solutions based off of 3 of our products in our portfolio: the DGX1, the DGX2, and the DGX2H. The DGX1 has been a platform that's been around for 2 or 3 years now, and it is a 3U chassis that consumes about 3,200 watts. And it has 8 GPUs in it that are at about 300 watts apiece. The DGX2H was announced about 2 years ago now, or sorry, about a year ago now, and it has 16 GPUs and takes advantage of NVLink technology. The GPUs in that are 350 watts. For this Circe supercomputer that was created for part of this ML-Perf submission, we went and turned the knobs up on it and created a DGX2H. So that solution has 400+ watt GPUs in it. So within a short amount of time, our power consumption on a GPU has gone from 300 to greater than 400 watts within our GPUs. One of the other things that you can notice on the Circe version, or the 2H, is that the inlet air temperature went down. So as you start looking at the effects of machines like this in a data center, it drives the desire for that level of intelligence, or for a greater level of intelligence in the power distribution. So if you were to start deploying these in a data center, you often go and look at what that PDU is capable of delivering. So from a first principles within a data center, you have a rack footprint that has a negotiated service level agreement for that rack can provide 8 kilowatts, 17 kilowatts, 34 kilowatts. There are different standards within the data centers. So looking back on Paul's slides, he showed there's a significant portion of those data centers that have less than 10 kilowatt capable compute racks. In those environments, you couldn't even put a single one of our 2H DGX2 or 2H nodes. With our DGX1 product, you could put n number of them in there to consume that footprint. So what I'm showing on this slide is that if you are in a traditional data center where you had about a 17 kilowatt footprint, when you put our higher capability compute nodes, the DGX2 and 2H, you start underutilizing the power that was delivered to that rack. So from a data center efficiency and control, that is not a desirable place to be in because you are stranding power in that data center. The middle column, I'm walking through an example of 34 kilowatts is kind of one of the next steps or a next common step within the data centers. So that is commonly seen in HPC, oil and gas, seismic processing kind of data centers. So that number is a pretty typical number. So that would start allowing you to get to better utilizations of the power that is being distributed in the data center. The third column is kind of a future looking. What if we had 100 kilowatt or 100 amp PDUs that were capable of 57 kilowatts? What would those solutions look like? And as you look at those, it's like, very interesting, but those are a challenge to do, air cooling on. There are some solutions out there that can do that, but air cooling them gets to be a challenge. So it puts another tension on the data center. When I think of the data centers, these are meant to be 3 columns and 3 types of cooling that you may see on each of those categories. So on the left side, you're seeing something similar to the Open Compute one on the top is an example that Facebook released publicly, probably 6-8 years ago. And that is a desire to have no chiller, and it is a desire to take advantage of evaporative cooling. So it's got a wetted material and a fan wall. In that environment, they have a very homogeneous distribution of air, so every rack location wants to have a similar air footprint and power footprint. So that solution has worked well for them for lower power racks. If you look at the picture on the lower left, that is more of a traditional raised floor computing space. In that environment, you have to push air from a craw unit, under a raised floor, and to get it in front of the racks. So all of these things are things that can be controlled through some of the Raritan products, but from an efficiency standpoint, you've got a longer path for air, and it's just hard to get enough air as the rack powers go higher and higher. The middle column is showing a containment or a closer coupling of air solution. So HPE has a product, their adaptive rack cooling solution that has a very optimized airflow path so that the air moves from the center of those 3 racks to the racks next to it, and they are capable of doing north of 50 kilowatts worth of air cooling per rack, and they have tight controls on the airflow. Rear door heat exchangers are examples of things that are very possible for the 17 to 35 kilowatt kind of energy footprints. We have many of those within the NVIDIA data centers for some of our solutions. And then cold aisle containment is another example. So that is fairly prevalent in a lot of the high performance computing environments. When you go north of 50 kilowatts, there becomes a very strong propensity to use water. So things like Summit and Sierra, which are the two biggest supercomputers on the planet, are using direct water to the chip. So they have 6 volts and 2 power 9 processors. The largest AI supercomputer in Japan is called the ABCI. It is using 4 V100s and 2 Xeons, and it is water cooled. So from the hyperscale data centers today, they look more like what's on the left. The supercomputers of the world look more like what is on the right. And as AI is an increasing focus, my belief is that the trend will be to pull some of the hyperscale data center solutions more to the right. So whether they stop in the middle or go all the way to direct water cooling, we'll see what the answer is or see how it works out. From an NVIDIA standpoint, we focus on the GPU. So from a monitoring of an application, it is very important to know how much power consumption is happening to do that task at every level. So whether it is the GPU, the CPU, the fans, the network switches, the InfiniBand switches, all of those things play a role. Our NVIDIA data center tools focus on the GPU only, and we have various libraries and tools. The NVML, which is a management library for communicating with the GPUs. The DCGM is a tool one level up that can puts a little more of a wrapper around it for managing the GPUs. But at the end of the day, there still needs to be a third-party application above it all that goes out and looks at the Raritan smart PDUs and the network switches and the CPUs and the BMCs to go get a holistic picture of what that energy footprint was for a task. So to go and get the level of AI at the data center that Scott was referring, there's a whole bunch of pieces or sensors to go and get this to happen. So GPUs are one of the big power consumptions, so therefore it needs special focus. So within that management tool, we have the ability to go and set a list of attributes. So sync boost, application clocks, memory application clocks, how fast the memory is going, whether you want to power limit the GPU or not. So if you look at some of the things that NREL had done in Scott's presentation, if you could go in and characterize all of those workloads with these at different settings, you could go and figure out which was the right set of settings to have a optimized energy consumption for a task. Because it's possible that we can lower the power limit and not have any effect on the quality or the time that it took for a job to run. If the job is often doing a hurry up and wait, that it was waiting on storage or waiting on networking, running the GPU at 400 watts may not have done any good unless you had everything else optimized so that the GPU was the bottleneck. If there's some other piece in the puzzle that's the bottleneck, then there are opportunities for optimization. So on the examples that I was showing before, the rack elevations were based off of the compute power requirements. So if you were running the heaviest workload on that node, it was consuming 3,200 watts or 10 kilowatts or 12 kilowatts. But there are lots of very valuable workloads out there that are not running it at maximum. So as a data center trend, we need to have tools to allow things to run at something less than maximum and have an efficiency value story. One of the tools that we have available is the ability to, so from an operational standpoint, before you kick off a job, you can reset a counter, you can run the job, and then you can, at the end of the job, go off and read the energy consumed in joules. So we can give this number down at every GPU level. So if this job took 2 minutes to run, or 2 hours to run, or 2 weeks, this number will be different, and you can start putting an energy signature on top of it. With tools like this, I believe it is possible to paint a better picture from a data center utilization. So this example here is to take the same pieces of hardware and say, well, we know that we're not really going to run them at full speed all the time, or our workloads never get them to full speed, but we still need a control function to make sure that the circuit breakers don't trip. So in the Raritan products, they have the ability to go and send an alert if you're getting close to one of those circuit breakers tripping, which could go and kick off a job to go and cause the power caps to get reduced so that you don't trip a circuit breaker. The goal is always to get the most out of it that you can. So whether it's the most out of the data center power distribution, or the PDU, or the compute, it's all about how do we get the most out of it. In this example, I did simple math on it to say that each node had the same average power. There's no reason that you couldn't come up with a strategy where one of the nodes, or 2 of the nodes, or some number of the nodes were running at max, whereas the other 40 or 60% of the nodes were running at a max Q. So NVIDIA publishes documents and settings to help you get to max Q. Max Q is the point at which a GPU is the most energy efficient. So the energy efficiency is actually a function of job type. So if it's heavy memory usage versus computationally intense, that number moves around a little bit. So there are so many innovations that are happening today in the ML world, it's just hard to predict where that number is going to be for a future algorithm that doesn't exist yet. Because with the level of innovation that's happening, the answers are going to change. So therefore, it is the most important for us to start having control paradigms to go and look at this and to put a structure around how do we get the most out of it. So one of my first slides where I had the rack elevations, that wasn't a very economical thing from a data center point of view. Stranding that amount of power within a 17 kilowatt rack isn't a wonderful thing, but getting the instrumentation and control so that we can get up to a full utilization of, whether it's a 17 kilowatt cord, or a 34 kilowatt cord, or a 50 kilowatt cord. So it's all understanding your workloads, and to be able to understand your workloads, you need to be able to measure it and metric it. So this is kind of a high-level list of trends that I see in the ML space. So in the ML space, a single CPU kind of model I don't think is going to win. It's a hybrid node of a CPU and a GPU. So GPUs that are tightly interconnected work better together. So scale-up nodes are a key part. Higher power nodes, when you have those higher power nodes, it does have the negative effect of it has the potential of stranding within a PDU. To control something, you need to be able to measure it. So it is important for the industry to be thinking about how do we go and create the right tools and the right plumbing to be able to measure and control these things and come up with the standardized alerts of when we're about to trip a breaker or when we can't maintain a thermal, and to be able to feed that back into the job scheduler that can go and use DCMI, our data center monitoring tools, to go and set the GPU into a different mode. The physics of all of this has, the power consumption going up. My belief is that water cooling is going to be a growing part of the solution. It's already there in the high-end supercomputers of the world. My belief is that it starts happening in more and more places. It is being largely driven by networking and GPU workloads. That's all I had for today. Appreciate your time.
Okay, great. Looks like we do have a few questions, but just a reminder to the audience, feel free to submit any additional questions you may have. So let's go ahead and get started with our first question. Why would you recommend not moving cooling to a single-phase dielectric fluid cooling solution rather than using air or water?
Single-phase dielectric cooling are interesting solutions. There are physics that say it's an interesting answer. A lot of this gets into the total cost of ownership. So there are lots of research going on and passions about this. Some of these get into what level of networking is required. The single-phase dielectric materials are often not friendly for high-density networks. So water is just my first choice, but there will be others.
Okay, great. I was once told by someone in the power industry that when a data center is highly likely to host ML workloads, you can pretty much forget airflow only as a cooling strategy. But whenever we add liquid cooling to the discussion, some folks entertain a train of thought that rack densities can go up because Ling substitute for a comprehensive airflow strategy?
So from a liquid cooling standpoint, the minute you go to liquid enables kind of a 10x increase in density. Whenever the cooling is one piece of the puzzle, the control and fault control is the other piece of the puzzle. So if you are hooking up, for example, so to put in the appropriate controls for a 10 kilowatt water-cooled rack versus isolation for a 50 kilowatt rack, the numbers are not, let me rewind a second. So hooking up water connections, there is a tax for that. Hooking up, whether those are capable of 10 kilowatts of cooling or 100 kilowatts of cooling, that tax isn't linear. So you want to go to kind of the sweet spot based off of your fault isolation on a cooling interconnect. If a cooling line fails, you don't want to take out half of your service, for example. You need to have enough resiliency in your service so that a failure or a fault can be isolated, controlled, and you can still deliver on your service needs.
Okay, great. The next one is kind of a two-parter. How does direct water cooling work, and how effective is it?
So direct water cooling has been around for decades. Mainframes used it 3 or 4 decades ago and still uses it. So originally, as you put direct water cooling closer to the chip, there are inherently more costs associated with it from an upfront standpoint, but from an energy efficiency, there are many, many models that show that you get those cost savings back. One of the big issues is, what is that connection tax? So if you have a 200 watt node, for example, and you're trying to water cool it, all of the connections that you need to put in there for water cooling a 200-watt node, it's actually very hard to get that energy savings back. You added more cost for those connections, but they're on a small node, the value may not have been there to do that. So a lot of the hyperscale data centers made the right decisions at the time that they created their data centers, that on a 200-watt node, air is the best answer, or air is the most cost-effective answer with the TCO. We are now, 10x those densities. A 3 kilowatt DGX1, for example, can easily, the TCO math easily works for that solution to be water cooled and have a value prop. But it gets into a question of, are there enough data centers out there that have water that could take advantage of it? So it all becomes a business TCO. And as the numbers keep going up and up, the TCO math is going to get easier.
Okay, great. Next question. Besides Google's AI/ML initiative to optimize PUE, who else in the industry is leveraging AI/ML for addressing data center issues? Are there AI tools available that are designed for data center use cases?
Yeah, that's a good question. There are a few companies out there that are currently doing this. It's really currently about integrating some of this into the DCIM portions of their tools. So kind of taking all of that data that they're gathering anyway via their DCIM, and then applying some machine learning practices to it to ultimately optimize things. Some names just off the top of my head, companies like Litbit, Adept DC, Vigilant. I'm sure there's others, and there may also be components of existing DCIM platforms out there that have that capability.
I think we're in the early days of being able to reliably apply all the data that we're collecting in the data center to give us real answers about how we can more effectively utilize power. I think in the near term, though, we're learning more, we're becoming more aware of the nature of power consumption and what specific triggers drive more or less of it. As we continue collecting that data, eventually there's going to be this aha eureka moment that, okay, I see a correlation between this pattern and this level of savings. And once that is discovered, there's going to be a whole new wave of commercialization. You're going to see DCIM try to take advantage of that. There will probably be a new wave of kind of smarter DCIM, but we're not there yet. I say look to 2020 as maybe the earliest we'll see that kind of breakthrough.
Okay. What is the trend in GPU energy efficiency independent of cooling approach? Is there an estimated improvement over the next 3 years?
So a lot of it gets into how you're measuring efficiency. From a efficiency of a cost per flop, as silicon technology evolves, the cost per flop goes down, or whatever that operation is. So yes, GPUs are going to move to next silicon technology, and then it gets into how efficiently are all the frameworks using them. So there is, a fundamental, physics at the silicon level, then there is a software deployment level, and then there's the cooling. The cooling has kind of two levels of effect, but I want to call those a small double-digit number in the efficiency. The silicon change and the software changes have the ability to make huge difference in the efficiency of solving a problem.
Okay. Where are the AI and ML algorithms running? Are there dedicated CPUs/GPUs that are collecting the monitoring data and control the application processors?
I think it's it's early days of seeing these type of algorithms running inside the same data center that's being monitored. I think if folks recall the famous Heisenberg uncertainty principle with respect to subatomic physics, when you're observing a situation, you can't help but interfere with it and thus changing it. When you're monitoring power consumption using AI in your own data center, and you're using an algorithm in the same data center, you're creating a heat source and then you're interfering with the solution. So it's no longer a blind test. So I think a lot of institutions and enterprises are saying, okay, instead of doing it that way, let's outsource the AI part of it to the cloud. And thankfully, there's a lot of good cloud-based AI out there. We mentioned Google Cloud AI is a pretty good example. And certainly there are ways that developers or software developers are learning to use what's available in Microsoft Azure and Amazon AWS as well. What they're doing is they're absorbing a lot of the data that's being collected in real time and generating heuristic analysis from that. And that's one of the reasons you're seeing some of the big cloud companies actually acquiring analytics companies, is because, hey, real-time analysis is pretty necessary, and there's a reason to outsource it and stage it somewhere else. So right now, I think at least in the next couple of years, we're not going to be running AI-equipped monitoring in the data center that's being monitored.
Yeah, I mean, and it's gonna take some time to kind of build up all of these data sets as well. Like Google, for instance, it took them 2 or 3 years to actually collect all of the data to actually start performing some of these operations. So it's going to take some time for all the intelligent PDUs and environmental monitoring sources of data to collect all the information that they might need to build training algorithms around this.
Okay. Looks like we have time for a couple more questions here. Mike talked about a continuing propensity for over-appropriating power to certain racks and then stranding the unused portion of it. How pervasive is this trend in the high-performance computing category, particularly with workloads like machine learning compared to the more general workload categories handled by enterprise data centers and colo facilities?
So the stranding of power, everyone works this slightly differently. So from the HPC workloads, they often go through a rigorous RFP process, and they will know that these are our 8 apps or N number of apps that are important, and then there's another set of apps that are less important. So at NVIDIA, we have what we call the value calculator that helps characterize, what apps should be optimized on that GPU node. So in the high-end HPC space, they have been very. One of the quotes a friend of mine basically said, "If I'm not running my machine at 80% utilization, they take it away from me." In the hyperscale space, they're often happy with utilizations in the 40% range. So they don't necessarily look at the stranded energy part. They have a larger scale so they can go and place jobs on it. But to place those jobs, they have to take advantage of understanding what that energy signature is. So it's a question of how do they market it, how do they sell it, and what are the quality of service inside, or the quality of service required for the users.
Okay, great. Well, it looks like we're just about out of time today. But before we go, I'd like to thank Raritan for sponsoring today's event, as well as Scott, Paul, and Mike for your great discussion. Just a reminder, the seminar will be available on demand starting tomorrow, so please feel free to come back and review. Have a great day, everyone, and thank you for attending.
Thank you, everyone. Much enjoyed it.
Thanks, everybody. Goodbye.
Take care.